All right, so we're going to continue looking at Chapter 5. So we did 5.1 last time when we had class on Thursday. Now we're going to look at 5.2, bisectors of a triangle. Okay, there's two kinds of bisectors we can look at. Segment bisectors and angle bisectors. Okay, let's start off with the bisector that's going to have to do with a segment. Okay, specifically, we're going to talk about a perpendicular bisector. What does it mean to be perpendicular? If something's perpendicular to something else, then that means what? Ian?
When a line crosses another line, it forms 4 right angles.
Okay, so yeah, if two lines are perpendicular, they form 4 right angles. Yeah. So the idea here is if two things are perpendicular, you form a right angle, or 90-degree angle. And bisector, okay, we just said that a second ago. What does it mean to bisect something? Right, to cut it exactly in half. So a perpendicular bisector of a triangle is a segment, a line, or a ray, be any of those things. But what it has to be is perpendicular to one side of the triangle and it has to go right through its midpoint on that side. Remember the midpoint, that's the point that would be the halfway point on a segment. Okay, so perpendicular bisector, it's a line, ray, or segment that's perpendicular to one side of a triangle right at its midpoint. Any question on that definition? Okay, and what we're going to do is we're going to look at drawing all 3 perpendicular bisectors, because you can draw one for each side. And something special is going to happen when we draw all 3 at the same time. Okay, if you have 3 or more lines, okay, and they all intersect at the same point, there's a special name for that. Those are called concurrent lines. Okay, you've got 3 or more lines that all intersect at the same point. Those are concurrent lines. And the point where they all meet, that's called the point of concurrency. Today we're going to talk about 2 different points of concurrency. One of them is going to have to do with segment perpendicular bisectors, and then the other one is going to have to do with angle bisectors. All right, so first fact. If you draw the 3 perpendicular bisectors of a triangle, they are concurrent. Okay, remember, concurrent means that they all meet at a special point. All right, let me show you an example. Okay, here's an acute triangle. Okay, I've drawn 3 red lines. Each red line goes through the midpoint of one of the sides, and the red line also forms a 90-degree angle with the side, right at the midpoint. Okay, and if you sketch it reasonably accurately, we can see that there's a point of concurrency. I labeled it point P, right there. Hey, any question on that? So notice for an acute triangle, what does that mean if it's an acute triangle? Yeah.
All the sides are less than 90 degrees.
All the
angles are less than 90 degrees.
Yeah, all the angles are smaller than 90. Okay? So for an acute triangle, the point of concurrency is inside the triangle. Let's see what happens when we go to a right triangle. Okay, here's a right triangle. drawn in again three lines, the best I can, going through the midpoints and all perpendicular to the side that they're going through the midpoint on. And notice the point of concurrency this time, it ends up being on the hypotenuse, if this was a right angle. So it ends up being on one of the sides of a triangle. What do you think is going to happen if I draw an obtuse triangle? Where do you think that point of concurrency will go if we kind of continue that pattern? So it was inside the triangle, it was on the edge of the triangle. Yep.
Off the triangle.
Yeah, it's going to be outside the triangle. Okay, so that was our acute triangle, right triangle. Here it is for an obtuse triangle. Okay, so again, three red lines, each going through the midpoint and perpendicular to the side that they go right through that midpoint. And the point of concurrency ends up way up there. Okay, any question on that? All right, so let's take a look at a few special properties and what that point is called. So the point of concurrency, okay, for your perpendicular bisectors of a triangle, that's called the circumcenter of the triangle. Okay, we're going to be learning about, I think, 4 total different points of concurrency. We'll do 2 today and 2 tomorrow. So it's good to try to keep a list of what all these things are called, so if I ask you on the test, you know what they're called. All right, so the point of concurrency for your perpendicular bisectors, that's called the circumcenter. All right, and let's look at a theorem. Okay, this will be theorem 5.5. It's on, let's see, page 273. It's a theorem about your perpendicular bisectors. It says that the circumcenter is equidistant from the vertices of the triangle. So once you mark that circumcenter, the distance from that point to every vertex in the triangle is exactly the same.
Even if it's off the triangle.
Yep, even if it's off the triangle. Okay, let's go back. Okay, it's going to be, it's not, my triangle is not perfect, but let me try to do this the best I can. So from that point to that vertex, okay, let's take that segment, put it over here, and I want to be able to rotate it, so I need to group it with something to do that. Then I can erase it. Okay, so we've got that one. And let's measure from a point, okay, to another vertex. Let's measure from there to there. Let's take that segment, and let's just compare those 2 lengths. Okay, again, might not be quite perfect, because, but they're pretty close. I don't have them turned exactly the same either. But if you used a protractor, or even better, a compass and a straight edge, you could construct this perfect. And that third distance would also be the same as the other 2. Yep, even if it's off the triangle. And another special property is that the circumcenter is the center of a circle that would pass through the vertices of the triangle. Okay, let me show you what I mean. Okay, let's draw a circle with the circumcenter as the center of the circle, and watch what happens. Okay, if I can, let's try to position it. I was a little bit off, but not bad. Okay, my sketch isn't perfect, but it's close. That circumcenter, that's the center of the circle. And that circle goes right through the 3 vertices of the triangle. This one, and that one. Okay, even for even for this obtuse triangle, that would work. It would end up being a very, very large circle. Oh, it's a little bit off, but let's see. See if we can position it. It's about as good as I can get it. But it goes through the 3 vertices of the triangle, and it's the center. Okay, any question on that? Okay, so there's all kinds of applications to that. Why would you want to be able to sketch a circle that goes through 3 vertices of a triangle? I'll show you one later. We'll look at a word problem that's going to use the circumcenter to do something. And there's another example of the same thing I just showed you. Okay, any questions on that? Okay, so make sure you understand that idea, because we're going to look at another circle today that's similar, but it's not going to go through the vertices. Okay, so the circumcenter is the center of the circle that goes through the vertices. Right. Let's see where that could be useful. Okay, so it says a company is planning to build a distribution center, and they want the distribution center to be convenient to 3 of its clients. Okay, so maybe the clients have to go to this center, pick up the materials they need, and then bring it back to where they are. Now, what we'll do in this diagram is assume all other things equal. Okay? Assume that the roads between all the distribution centers and clients, they're all in the same condition, so they don't have to travel at different speeds. Everybody could travel at the same speeds on the roads, all right? So we won't assume anything complicated like that. So I want to know how the circumcenter, why using the circumcenter as the location for the distribution point? Why would that be the best way to do it? So they had a map or a grid of a city, and they, sketched it out. And, maybe they couldn't get it perfect in a real city. That could be a river or something. But they try to, get it pretty close to the circumcenter. Why is that going to be the best location, assuming all else equal? Yeah?
Because it's the center. Because it's, we draw a circle from the center, and that would be that we're assuming that A and C is the same as B and C and A and B. So if it's the center, it's the same distance apart than the other ones.
Well, I heard you say that A and B and A to C were the same, but we don't know for sure. We don't know that the distance between the clients are the same. But we're kind of getting there.
The
Luke?
circumcenter is equidistant from the vertices, and the clients are the vertices.
Exactly, yeah. Your clients are basically the vertices of a triangle. Okay? And if you want a point that's equidistant from all your clients, that would be the circumcenter, because the clients are your vertices. Okay, we'll write that down. So clients are the vertices, and the circumcenter is equidistant from the vertices. Now, in real life, there might be a few more things they have to take into account. For example, suppose that from A to the circumcenter they had a highway, and B to the circumcenter it was just a back road. Well, in terms of the time, maybe you want to have it a little bit closer to client B, because they can't drive as fast to get there, because client A can drive faster. Okay, so there might be other things. And if you have more than 3, then the problem gets a little bit more complex. If you had 4, you can't just connect them and make a quadrilateral and figure it out as easy. Okay? Or even worse, if you had 5, 6, or 10, even more. Okay? But for 3, it's pretty easy to figure out. 2 is also very easy to figure out. That's just your midpoint. Okay. Okay, so now it says to sketch the triangle. Okay, we already did that. Formed by, well, I used points A, B, and C. I'm sorry. And now I want to try to find the circumcenter. Okay, we'll do this the best we can. Without a compass and really taking a lot of time to measure, it can be tough. Right, so let's try to find our midpoints. Okay, so maybe right about there. Try right there. And right about there. Okay, anyone disagree with those as the midpoints? They look pretty close. Right, let's try to draw in our perpendicular bisectors. Let's try again. Okay, so we're trying to make that angle as close to 90 as we can. So there's one. If it doesn't go through the midpoint, I can fix that after. Let's try that. There's 2. And I think we're going to be pretty good. Third one. It's not perfect, but it's pretty close. So there's the circumcenter. So that's about where you'd want to put the factory. And it would be equidistant between all 3. Okay. Any question on that? Okay, so there's one use for the circumcenter. All right, now let's figure out which segments in that diagram are congruent. Right, to do that, I got to label a few more points. Let's call this point D, E, F, and center G. Let's see. Yeah, okay, so which segments there would be congruent? I might not have them all sketched, but now you've got some points. Which segments would be congruent if we were to sketch them? Connor, can you just give me one?
BF.
B to, well, that's on the side. It's from the vertex to the circumcenter. So B, B what?
E.
B, no, not B to E.
is congruent to itself. Reflexive property.
So we need our segments from the vertices to the circumcenter. They're not actually sketched in the diagram. But go ahead, Marquise.
G.
Yep, GD would be congruent to what?
GF.
Let's see. Yep, GD to GF, yep. Which would be congruent to
GB.
the last one? GB. Good. Okay, so we've got G. Oh, did you say D? No, GD is wrong. No, GD is not right. Anybody fix that one? G. Oh, you know what? From the vertex to the center. Let me go through it. GB. From the vertex to the circumcenter. Then from, let's see, C to G. Again, that's from your vertex to your circumcenter. And from A to G. Those are the distances that are equidistant. Okay? So from G to client B, from G to client A, and G to client C. Those are your ones that are congruent. Okay, so I don't think we actually needed points E, F, and D labeled. But we will for the next part we're going to do. Okay, any questions on on that? Okay, if you wanted to name some other segments, there's all the midpoint ones, so you could talk about AF and FB, those are congruent, BD and DC, and AE and EC. Okay, we don't need to mention all those. I don't think that's what they were getting at in this problem. Okay, any other questions on that? All right, so let's look at a different point of concurrency. Okay, this is going to be the angle bisectors. So this time we're going to cut angles in half rather than the sides. If you draw in all three angle bisectors, they will all intersect at a special point. They're all going to be concurrent. And the name of that point is called the incenter. Okay, that's the incenter. Okay, the incenter is always inside the triangle. Okay, we saw for the circumcenter, that's not true. It could be inside, it could be on, or it could be outside, but not the incenter. Incenter is always inside. Okay, let's take a look at Theorem 5.6. Okay, so that's page 274. So the incenter is a point that is equidistant from the sides of the triangle. Okay? Not from the vertices, but from the sides. And the incenter is also the center of a special triangle, special circle. This time it's a circle that if you draw it, the circle ends up being inside the triangle. Basically, it's the largest circle you could possibly fit inside a triangle. So let's look at okay, so what I'm going to try to do is draw in all three angle bisectors. It's just going to do it by eye. One. There's two. And our third one. Okay, so in this picture, those two angles are equal. Those two angles are equal. And those two. And that point that I just marked, that is your incenter. So the incenter, if I drew it accurately, it should be the center of a circle that can be inscribed in the triangle. That means the circle is as big as you can fit because it's going to be touching all three sides of the triangle. That one came out pretty good. So it's the biggest possible circle you could fit inside that triangle. Okay, any questions on the difference between that circle and then the circle we did before that goes through the vertices? So the radius of this circle is the distance from the center straight to the side of the triangle. So remember, if you're going to measure the distance for something, you want to measure it straight. You want to measure it perpendicular. So if I was going to measure my radius to the side of the triangle, I measure it about like that. Where that's a 90. That's the radius of that circle. To the side of the triangle. Okay, here's another example. Make it over here. Okay, pretty much the same thing I just had on the other page. Okay, any question about the incenter? All right, so what we'll do is we'll use this to actually do some calculations, right? We'll find the lengths of different segments. We might use some congruent triangles here, okay? Because we know a little bit about some of these theorems and distances and segments that are equal now. Okay, so in this one, I want to know which segments are congruent. Okay, in that diagram, which segments are congruent? Okay, first, looking at point L, what's the name of that? Is that your incenter, or is that your circumcenter? That's the incenter. Remember, the incenter is the center of a circle that's inside the triangle. Circumcenter, that's the center of a circle that goes around the outside of the triangle through all the vertices. All right, so we've got our incenter. And I've drawn in the 3 radii that are perpendicular to each side. It's LQ, LS, and LR. Which segments would be congruent in that picture? Yeah.
LQ, LR, and LS.
Yeah. LQ, LR, and LS. Those are all radii of the same circle. By definition, all the radii in a circle are congruent. LQ, LR, and LS. Okay, any question why those are congruent? How about, let's look at it the way we did with the circumcenter problem. How about the distance from each vertex to L? Would NL, PL, and ML, are those congruent this time? What do you think, Selena? No, not this time. Okay, that only works for the circumcenter. Okay. How about, let's see, if we look at MS and SP, are those segments congruent?
Yes. Actually,
No. That radii is not drawn to the midpoint. Okay, so same with point Q. Q is not the midpoint, and R is definitely not the midpoint. Anybody have a thought what kind of triangle the incenter and circumcenter might be the same point? Certainly not in this kind of triangle. Yeah?
Equilateral triangle.
Yeah, if you were to sketch an equilateral triangle, your incenter and your circumcenter would be exactly the same point. Equilateral triangle, there's a lot of overlap there. Okay, but we'll look at that once we, when we get a couple more points of concurrency tomorrow. Okay, now I want to find LQ and LR. Well, once I find LQ, I automatically have LR because they're congruent. All right, so let's see if we can find LQ. Anybody have any guesses how we could find LQ? Think about what shape are we really dealing with there to try to find LQ? We don't have to deal with that whole picture. We just have to deal with a small part of it that makes a certain shape. Yeah?
Just the triangle, like the bottom left corner of the bigger triangle.
Yeah, really just dealing with a triangle. Okay, you're trying to find LQ. And what kind of triangle is LQ in? It's a special triangle.
Or right triangle.
Yeah, it's in a right triangle with segment MQ and ML. So if we know 2 out of 3 sides in a right triangle, how can you get the third side? I think we did this last week. Yeah. Yeah, the Pythagorean Theorem. So square one leg, square the other leg, add them up, and that's equal to the hypotenuse squared. What are we solving for in this problem? A leg or a hypotenuse? Yep, we're solving for a leg. Okay. So I don't know one of my legs, but what's the other leg? 15. So let's let that be A. B, we can let that be the length of LQ. Okay, we don't know that. So 15 squared plus B squared equals 17 squared. I think on the MCAS simulation, there was a question like this too, about a ladder leaning up against a house, or something like that, and you had to find how high the ladder could reach. Okay, let's go through and solve it. So you get 225 plus B squared equals 17 squared. Okay, so 289. Okay, Katrina, how do I get the 225 on the other side? Yep, I'm going to subtract it. So 289 minus 225 leaves me with 64. And someone else tell me, how do you get rid of the exponent there? Yeah. Yep, square root. Square root. And can you go ahead, Selena, tell me what B is? Yep, B is 8. 8 units. Okay, so now we know the length of LQ, which we called B, is 8. How about LR? How long is LR going to be? Well, Alyssa? Yeah, that's also going to be 8. We said earlier LQ and LR were congruent, so they have to have the same measure. Okay. Do you think we have congruent triangles in that picture? For example, if you looked at triangle MQL and then the one next to it, let's see, MSL. Think we have congruent triangles? Yeah, Luke?
One angle is the same on the other side, and then the angle for the the line for LS is congruent to the line QL, so that's 8. So you got side, so the triangles are congruent through side angle side.
Yeah, there's all kinds of ways to prove they're congruent here, but I think they are. Because the 17 is reflexive. As Luke said, the QL and the SL match. And we know we have right triangles. So you could use the hypotenuse leg theorem. Okay. Once you prove it with the Pythagorean theorem, you could find that the third sides, MS and MQ, they're both 15. Gives us all kinds of congruent triangles. Okay, several pairs of them in this picture. Wait, any question on that? Okay, so looking at point A. Who can tell me, is point A the incenter or the circumcenter? Luke? Yep, it's the incenter. The reason you know that is the segments that I've drawn, I showed them as angle bisectors. All right, so why don't you take a minute on your own and see if you can find the length of AB. And that idea of congruent triangles, that might be handy here. All right, so see if you can try to find the length of AB. Okay, so they want us to find the length of AB. Okay, technically right now we don't really have enough information to find AB directly, but if we look at, let's look at the triangle that it's in, ABD. Which triangle would that be congruent to? Try to name the letters if you can in the right order. So ABD would be congruent to, yep, ACD. So if we could find the length of AC, then that would be the same as the length of AB. Okay? And we can. AC, we have enough information to find. Okay? What kind of triangles are we dealing with here again? Yep, right triangles. And what we're going to do is look at this one right here. Okay, and see if we can find the length of AC. What's the name of the theorem we use again to do it? Yep, Pythagorean Theorem. So a squared plus b squared equals c squared. And can somebody fill it in for me this time? Tell me what A, B, and C would be. Obviously, one will still be a variable.
A is 4 to the second.
Okay, so we got a leg squared, 4 squared, yep.
Plus B is second.
Yep, so we'll leave B to the second because B is a leg. We'll call segment AC, that's our leg.
A equals 5 squared.
5 squared. It's pretty much exactly the same problem we did last time, except now I'm asking you to kind of apply it to congruent triangles and find a length on the other triangle. But it's really the same thing. So we get 16 plus b squared equals 25. So when you bring 16 to the other side, b squared will equal how much? Yeah, that's equal to 9. Okay, and as somebody said last time, take your square root. That cancels out the square. And square root of 9 gives me 3. Okay, so now we know the length of AC. But AC is congruent to AB. And that's what they really wanted. So AB is 9. You don't have to write a formal proof. Sorry, 3, thank you. So you don't have to write a proof formally that these triangles are congruent. Just using what you already know and then doing out the Pythagorean theorem. Okay, any question on that? Okay, so what's the name of the point where the 3 perpendicular bisectors all meet? Yep, that's the circumcenter. And what's special about the circumcenter? 2 things. One, you could talk about the circle, or you could talk about the distance from certain points.
It's equidistant to all the vertices.
Yes, the circumcenter is equidistant to all the vertices on the triangle. So all those segments are congruent. And because you had to construct it using midpoints, you created 2 pairs of congruent sides, or congruent segments on each side, okay? Right between the midpoints. All right, so there's your circumcenter. And what's special about the circle? The circumcenter is the center of a circle that would do what? Yep.
That passes through all the vertices of the triangle.
Yep. Be the center of a circle that passes through all the vertices of the triangle. Where can the circumcenter be? The location of it. Does it always have to be in a certain place, or do we have options?
I'm sorry, an acute angle would be on the inside. Acute triangle would be on the inside.
Yep.
Obtuse would be on the outside, and the right would be on
Yeah, good. Everybody hear that? So for an acute, it's inside, obtuse, outside, right triangle, it's right on one of the sides, the hypotenuse. Right? So that's all the characteristics of your circumcenter. Okay. How about, what's the name of the point where the angle bisectors meet? That's your Marquise?
In-center.
That's your in-center. Yep. And what's special about the in-center? Who can tell me a couple things about that? Yep. Here. It's always inside the triangle, absolutely. Okay. What about the circle that it's the center of? How would you describe that? Yeah.
It's the center of a circle that fits inside of the triangle, the biggest circle.
Yeah,
that you would think.
exactly. It's the center of the biggest circle that you could fit inside the triangle. In other words, the circle will touch all three sides of the triangle. Okay, the fancy word for that is tangent. It's tangent to all three sides. Okay? And also we get one more fact here, that the distance from the in-center to each side, those are all congruent. Okay, those segments are all congruent. So AB, AC, and I didn't label it here, but A to E. Okay, they'd have to be, because they're all radii of the same circle, and all radii are congruent. Okay, so any questions on circumcenter and in-center? So if you're making a cheat sheet for the test, what I would do is put those two on it, and then tomorrow we're going to add 2 more. So once we add 2 more, it's kind of hard to keep all of them straight, but just make your cheat sheet and you can use that on the test.
How do you draw the in-center?
How would you draw it?
Yeah, like how do you show where it is?
So the only way to show it is if you get your triangle. Okay, something like that. Draw in all your angle bisectors. Okay, like that. Let's see, about like that. And like that. And the way that you show that it's an in-center is you mark those angles congruent, and those angles. That's the in-center. And the reason I know is because it's where all the angle bisectors cross. And I know because of the way you labeled it that they're angle bisectors. Yeah. And now if you sketch your circle, okay, depending on how good of a sketch you made, it should be the center of the biggest circle that just fits inside there. Mine was a little bit off, but that's a basic idea. Okay, any other questions? All right. So for tonight, the homework's on 275. It's 5 to 9 odd, 10 to 14 all, 16, 17, 20, and 22.